I'll also not be in engineering physics next week, so I need to take a test on Monday.
Monday? You're not gonna be here Tuesday? Might have the test ready on Monday.
I mean, I can take it after. I just didn't think you want me to take it.
I actually prefer taking it ahead of time. I will try and have the test ready. Okay. All right. So, do you guys see the document camera over there in the Enid? No? All right. Now we'll see. How about now? Yeah. Now it will. Now we're good. Now we're good. Okay, so we're still talking about projectile motion. We talked about circular motion. So what I'm going to do is work on a couple of things. This chapter in this book actually introduces the concept here, and that's relative motion. And this is, I am not a high energy physics person. Yes, I can do quantum mechanics. I don't like quantum mechanics. It makes me think funny. But we do still need to talk about relative motion. But this isn't relativity like Einstein's relativity. This is relativity like we all experience. So I'm on a train car. Okay? I've got a flat car on the train. And if I'm on the flat car on the train, and let's say this flat car on the train is traveling at 5 meters per second, because it's going to be slow. We're just going to use it slow. And I've got a person over here that's not standing on the train, okay, that's standing on the ground. And I'm walking on the flat car in the same direction as the flat car is moving. And let's say I'm walking at 1 meter per second. This person who's watching me walk on the flat car is going to see me traveling at 6 meters per second. That's how I'm going to appear to be traveling to the person on the ground. So me relative to the train car is just 1 meter per second. The train car going this way is 5 meters per second. But these velocities, so this is the velocity of that person plus the velocity of the train, is going to give me the relative velocity that this person is actually seeing. Okay? So that's when we start talking relative velocity. Similarly, we can look at it from a different perspective. If I'm on the train car, okay, train car still moving at 5 meters per second. Oops, can't write that. 5 meters per second. And I'm walking that direction at 1 meter per second. This person is going to see me walking what appears to be 4 meters per second in this direction. Again, because velocities have direction and magnitude, this ends up being subtracted out versus going forward. And we've seen this before, right? I mean, if somebody is walking 5 meters per second in this direction and the car is moving 5 meters per second, 5 meters per second, the person that's looking here is going to look like I'm standing still because I'm not moving forward until I hit the wall on the back of the train car or fall off, right? And so it's something we've experienced over and over again. And this is what?
You could compare it to like passing people on the interstate too.
Yep.
And like when you try to go on an escalator, go the opposite direction.
You got it. So the two examples is passing people on the highway. The other example is an escalator, and people have played with it. Or you can watch the Caveman Geico commercial, and the guy's walking on the traveling sidewalk, right? And he's staring at the poster. So those are, so relative velocities are something that we've experienced numerous times. And our book brings relative velocity into it at the end of this chapter, I guess we're on chapter 4. So the test is next Wednesday, as we've discussed. It's next Wednesday, unless you've made prior arrangements. And it will cover chapters 1 through 4. I'm in the process of trying to get all grades in on everything. I still have a few things that I'm working on, but I'm working on it. So let's look at a problem here. We've got you are riding in a boat whose speed relative to the water is 6.1 meters per second. The boat points at an angle of 25 degrees upstream on a river flowing 1.4 meters per second. And we want to know what is your relative velocity to the bank. Okay? We want to know what is the relative velocity to the bank. So while you guys are writing that down, I'll make a couple of other announcements. I have posted on Blackboard a link to something called Flippin' Physics. It's mostly in one-dimensional motion. It's a little irreverent, which is great. Always love irreverent physics stuff. It's a little irreverent, but it does have a whole bunch of different little video vignettes on projectile motion. It has them on motion in one dimension, and it has a lot of example problems. So it does compare like the motion of just a dropped ball, the motion of a dropped ball that goes off the edge of the table. So it has a variety of different things in there. So it may help you guys. Again, sometimes seeing it with somebody else, or just the way they explain it, or even the day that I've explained it, it may make it click if you're having trouble in a particular area. So there's a bunch of little vignettes on that one, and that might help you out as you're trying to study. So we've talked about this before. When you get a problem, the first thing you do, so if you write out the problem, let's kind of talk about this a little bit. It might help sometimes to underline what you know. So we know we got a 6.1 meter per second. We've got 25 degrees upstream. We got water flowing at 1.4 meters per second. When you guys get my test, you know, the first thing is draw a picture. If the problem calls for it, draw the picture. So you know, we've read the problem, we get to draw the picture. So basically, I'm going to make the assumption that I've got a river that's kind of going like this. We've got water flowing in the river of 1.4 meters per second. We've got, I'm going to use this as my X direction. This is my Y direction. And I'm going to do my little boat with my handy dandy little artiste point of view. Nobody ever said I was a good artist. Thank goodness. And we know that relative to this axis, it's telling us that we're pointing upstream at a 25 degree angle. Okay, so this is just in here for reference. So I've got two vectors, and we've even talked about this. If I'm driving down the road and the wind's blowing, I got to steer into the wind, otherwise I'm going to get blown right off the road. So I know I have to do that. So we've we can look at the one of the things that we said, when in doubt, and while I'm trying to think about how to get started, it's easy enough to do, all right, the velocity in the y direction of the boat is going to be our velocity sine of the angle. And if I put that in as 6.1 meters per second sine of 25 degrees, that's going to give me 5.5 meters per second in the y direction. Then we can do it in the x direction. Velocity in the x direction of the boat is going to be the velocity cosine of, oops, sorry, I wrote the wrong down. If you plug that into the calculator, you're going to get 2.6 meters per second. So there's my 25 degrees, and that's my 6.1 cosine 25 degrees. That's my 5.5 meters per second. And this is in the x direction, and that's in the y direction. So I can write my vector of the boat in terms of its x and y coordinates. It's 5.5 meters per second in the I direction plus 2.6 meters per second in the j direction. Is everybody with me? You guys with me over there? You awake over there? Are you warm over there?
They don't have to do stuff over there?
Well, has anybody been into Harold today? Okay. Harold's having a little trouble with its heat. It's all right. Crowder's usually having trouble with its heat, so we're actually doing all right in Crowder today. And I always find Zoller to be a little warm. So I've got my velocity of the boat. So I'm going to rewrite it down here so that we have that. And you guys are getting more ice than we've got over here. Icky. Okay, and the velocity of the river, it doesn't have any velocity in the I direction, and it's going in the opposite direction of the boat, so I can actually put it down as 1.4 meters per second that way. So our relative velocity, the velocity that we're looking at, is going to be, we can do our 5.5 plus 0 in the I direction, and we end up with plus 1.2 in the j direction. And we can find the magnitude of that vector. It's just going to be the square root of 5.5 squared plus 1.2 squared. And if I take the square root, that's going to be 5.6 meters per second. Okay? And this makes sense because it's traveling upstream, right? So if I'm standing over here on this side of the bank, it's certainly not going to be going as fast as we anticipate because the water's pushing it backwards, right? And we all know this because if we've ever tried to swim upstream, we know how that feels. Right? We're getting that resistance that it's encountering. And now we also know that what it's going to do is I can find the angle. The angle is going to be the inverse tangent of my 1.2 divided by my 5.5. And that's going to give me 12 degrees. So we can actually calculate it, and we can actually calculate that vector. But if we want to draw this, because as we get into other things and we start looking at other pieces, here's the velocity of the boat, and I've got the velocity of the river like this, and then I'm going to ultimately get a resulting vector like that. And we just showed that if this one is 25 degrees, this one ends up being 12 degrees. This from here to here is 25 degrees. From the resultant vector to here is 12 degrees. That's what we calculated with the tangent. And we saw that the magnitude of this is 5.6 meters per second. And so if I'm standing over here on this side of the bank, the boat looks like it's going like that. That would be the path that the person on the side of the bank would see. And that is a relative velocity, and you can do a relative, you can also do that in acceleration, you can do it in forces, you can do it in a lot of different pieces, but this is why we call it what we have relative velocity. And I think you got a couple of homework problems, but I will tell you that I will not give you a relative velocity question on the test. I will give you vector addition questions on the test. I will give you vector subtraction questions on the test, but I am not going to give you a relative velocity question on the test. I see clapping. I see clapping. Yeah, I see clapping over in Enid too.
Why don't we have any of these? It'd be fun to have on a test.
Huh?
It looked like they'd be fun to have on a test.
They actually kind of are.
Spencer.
You should give us that
Come on
very,
now.
very first cliff problem you gave us.
Cliff problem? We're going to work a couple others today. We're going to work some more projectile motion problems. Yay! I love projectile motion. Projectile motion is fun. And projectile motion is practical. Let's be honest.
One that we haven't learned yet.
Projectile motion is
The
practical.
cliff problem just blew your mind just with everything that could be has.
Oh yeah. That's what we're gonna play. And in fact, do I have it? Yeah, I got it. We'll do this one today. We'll do this one next. I like projectile motions are practical, man. And the fun part about projectile motion is you guys have been doing it in your head since you were little itty bitty kids.
Not all the math. Therefore, you can visualize it.
Yeah, you can visualize it, and you actually can really pinpoint it, and you guys can estimate. Now, I will tell you when it gets really, really complicated. My daughter is an equestrian and jumps horses. Okay, that's what she does. She goes over those stupid fences, right? All right, think about this. She would go around an arena. She happened to work with the Olympic show jumper coach for a variety of things. So she's worked with an Olympic show jumping coach, and they put in the arena. They would put a dozen jumps in the arena. She would be going through, and he would be changing up the jump courses so that which jump you would jump over. She would be doing the projectile motion not only for herself and where she needed to be body position wise, where she needed to put the horse so the horse could take off and jump the jump so he could jump the next jump, what line to take, and then was still being able, you could ask her state capitals as she was going around the arena. So she's sitting here doing all of that mental calculus and mental calculation for doing projectile motion, at the same time answering questions about state capitals, not only for herself, but for her course. So we do so much physics in our heads that we never ever think that we could write down. And then we can write some stuff down, which is totally cool.
It's harder when you write it down.
It depends. It depends. So everybody got it written down? All right. So we're going to do the ski jump problem. Okay? We're going to do the ski jump problem. Okay, I love the Olympics. Winter Olympics was lots of fun. Summer Olympics is pretty cool, you know. And so we get lots of good problems that we can work on. So we've got a ski jumper that's going to come off the jump. The jump's going to be 50 meters. We're going to come off the jump. We're going to go down, and the slope of the hill looks like that. Okay, the slope of the hill looks like that. And let's see. So I've got a ski jumper that's taking the track, and he's moving a horizontal distance speed. It's coming off at 25 meters per second. So I don't want to write on my handy dandy picture, but we'll draw the picture in. So it's 25 meters per second, and the landing and the incline is coming off at a slope of, this one is using a slope of 35 degrees. This picture shows a slope of 30, but we're going to use the 35 degrees. And we want to know, where does he land? Down. If it's me just skiing, I go splat. All right. Let's just be honest. I go splat. I lived in Salt Lake for 4 years. I tried to learn how to ski 3 or 4 different times. It ain't happening. I can do cross-country skiing. I'm not doing downhill skiing. I am a danger to everybody on the slopes. So we're gonna be there. All right. So now the question always comes in is, what's our time? How do we deal with it? And do, you know, where are we going to end up? So we know that the origin here, that's 0, 0. And now we got to figure out where we end up landing. So let's
Where's 0, 0? The 5 meters or just
right here. This is 0, 0.
Yeah, right above the 5 meters.
Yeah, right above the 5 meters. So basically what we've got, so we you know, draw your picture, right?
Yeah, it's not a very good one.
So we've got, now the first thing that we know is we're coming off at 25 meters per second. We've got a slope over here, and we've said that this is 35. Well, this picture said 30, but I'm going to use 35. Because I've got ski jumpers, slopers from different problems, but my notes have 35 instead of the other. Okay. So things that we know, right? We know the acceleration due to gravity is 9.8 meters per second squared. Right? We know that my position this way in the x direction is going to be the velocity of the x times time. We know my y position is going to be my initial velocity in the y times time minus 1/2 at squared. Right? So, one of the things we're going to do in this problem that's a little different is wherever I land, so this is my landing spot, we can represent this as D, distance down the hill. So now let's look at this a little bit. So if I come over here, I can draw this little line here. That's 35 degrees. So y is D sine 35 degrees. We know that ends up being 0 because I have no velocity in the y direction. And I have minus g over 2 times squared. This one, that's d cosine 35 degrees is equal to my velocity in the x direction times time. That equation and that equation, these are independent. God, I can't spell today. Independent. And if they're independent, I have two equations two unknowns. So I have two equations, two unknowns. So here comes some fun stuff we can do, right? You can solve for two equations, two unknowns, a variety of different ways. I don't care how you do it. You might want to refresh yourself on how to do it. So with this one, I'm going to write this one on top first. D sine 35 degrees is equal to minus G over 2 t squared. I've got D cosine 35 degrees is equal to Vx times time. Now, if I'm wanting to solve for time, I've got a simple way to do it, right? Use the mathematical trick of this. D's cancel, one of my times cancel. I get the tangent of 35 degrees is equal to minus G over 2 Vx times time. Now this 35 degrees is in the opposite direction, which is why I've got a weird another angle that I've got to deal with, but I can account for that because my picture, my 35 degrees was up, so I'm actually upside down, but the magnitude's going to be the same, so I could solve for time at this point. So that's one way to do it. I really, really, really want D, right? So if I solve for time, I can just plug in and find D, but the other way to do it is this. I've got D cosine 35 degrees is equal to Vx times time. I can solve for time. Time is equal to D divided by V of x cosine 35 degrees. So now I take D sine the 35 degrees is equal to minus G to D Vx cosine 35 degrees squared. So now we can play with this. Good to get minus G D squared to Vx squared cosine squared 35 degrees. And then I've got D sine 35 degrees. And we can plug in numbers, make our lives a little simpler. Plug in numbers, let's see, sine of 35. This becomes 0.57D is equal to 9.8 divided by 2 divided by 25 squared times cosine, so I'm going to do it this way, 25 times cosine 25. If I put this into the calculator correctly, I get 0.064, there's a negative there, D squared. Divide both sides by D. I get 0.57 is equal to minus 0.064D. 0.57 divided by minus 0.0064 equals D. I get 89, negative 89 meters. Well, that's okay because we're landing below the surface. So this says D is 89 meters in the negative y direction. So that's good. So down on this hill, our skier is going to land 89 meters down the hill. Two equations, two unknowns. So if you want to brush up on two equations, two unknowns, we use it over and over and over and over again. We've been using it in projectile motion. I just didn't clearly articulate that it was two equations, two unknowns. Oh, let's do. We did the rocket problem. Let's do the basketball problem. Since we have Bedlam basketball tomorrow night, okay? We have Bedlam basketball tomorrow night. So I got my guy standing on free throw line. I'm going to actually do this in feet because my basketball court's in feet. The basket is 10 feet above the ground. I actually put this at, I think I've done this from half court, okay? I've got 47 feet from my person to the basket, 10 feet above the ground. We're gonna have it go off at, so projectile motion is gonna have it do this kind of a number here. I am not to scale. Not to scale, and we're gonna be 4 feet off the ground. And we're going to use that, the initial velocity that we're going to do is 50 degrees. And I want to know the velocity that I have to have in order to make the shot. Okay? I want the velocity that I got to have in order to make the shot. So, my change in x is going to be my velocity cosine of my angle times time. We don't know velocity and we don't know time. We know the angle and we know the distance, right? And then I've got a change in y is going to equal my initial velocity sine of the angle times time minus 1/2 gravity t squared. Two equations, two unknowns. Because we know the change in y. So the easiest thing to do here, right? The easiest thing to do is solve for velocity and put it in there. Or we can solve for time and put it in there. So I'm going to solve, I'm going to do this for, let's see, which way do we want to do it? Let's solve for time. So time is going to equal change in x divided by my velocity cosine of my angle. So now my change in y is going to equal velocity sine of the angle, change in x, velocity cosine of the angle, minus 1/2 g, and I've got change in x, velocity cosine of the angle, all that squared. So this becomes, that cancels, this becomes the tangent of the angle times the change in x minus 1/2 g change in x squared, velocity squared, cosine the angle squared, change in y. So at this point, it's nice to put numbers in just to kind of help us out. So our change in y is 10 feet. And then I get 47 feet tangent of 50 degrees minus 1/2. Here comes the fun part. if I'm doing gravity, this in feet per second is 32 feet per second squared. And watch out, because WebAssign will do this to you. Other things will do this to you, and you'll plug in 9.18 meters per second squared, and you'll go, okay, yeah, that makes sense. Not, because I'm in feet per second squared. And then I've got 47 feet squared. I don't know V squared, and I've got the cosine squared of 50 degrees. If I do that, plug that into the calculator. This becomes 56 minus okay, this is 35,344, and I'm in feet. Okay. I'm in feet cubed seconds squared, and that's got to be divided by the cosine squared of 50 degrees. And I'm 1 over V squared. And V squared, make sure that we're okay. V squared is in feet squared, seconds squared, so I'm ending up with a value that's in feet, so I'm okay. That's one of those things that you want to kind of check on. And this is 10 feet over here, that's 56 feet. So if I divide that by the cosine, I'm going to do this. Cosine 50 times cosine of 50. Okay, I got a weird number here. I get 56 minus 85,542, and I'm in feet cubed seconds cubed 1 over velocity squared. So now I'm going to take 10. So I'm going to take 10 feet minus 56 feet is equal to a negative 85,542 divided by V squared. This gives me a negative 46 feet is equal to a negative 85,542. V, multiply both sides by V squared, so I get V squared, and I'm going to take this 85,542 divided by 46, negative 46, divided by 46, gives me 1,1859. V is going to be the square root of that. .43 feet per second is what my velocity's got to be in order to make the shot. And then you can play with how long the ball's in the air. And you can do it with baseballs off a baseball bat. You could do it with arrows off of a, for archery. You can do it with Nerf guns. You can do it with pencils hitting the wall because you're frustrated with your physics problems. Yeah. Darts. We do lots of projectile motion. Lots and lots of projectile motion. I actually have it in my notes because I didn't have it the other day. My stats are that for your irons, 2 to 7 irons and things will run from 20 degrees to 27 degrees. And it doesn't matter which one it is. Okay, So, tests will be over chapters 1 through 4. I am going to start the next chapter on Friday, but that stuff will not be on the test. And there's a quiz coming up in WebAssign, so double check and look at when it's there. And I think I've got everything out there for WebAssign. So, yeah, the quiz is in WebAssign. Questions? You guys good over there, Enid? All right. Hang on, let me turn this one off. Okay.